So just so we're all on the same page, we did part 1, okay? And did we do part 2?
No.
Okay, thank you. So 2 and 3, we're going to come back to them.
There's a lot of the class.
Yeah, I noticed that. But we just did part 4, that's balancing equations. Wait, so is that what you guys get it in?
Yes.
So I hope you enjoyed them. Yay, and now we're ready for part 5. And I told you in lab yesterday that doing part 5 lecture is going to make your calculations that you need to hand in with your labs next week make more sense. So you guys balanced equations, and you did so by changing the stoichiometric coefficients in front of the species, okay, to get the same number of atoms, each type of element on either side of the reaction arrow. You balanced them. That was wonderful. So stoichiometric coefficients give what we call stoichiometry to the chemical equation. It's like a recipe. That's what I think. Stoichiometry is just like a recipe. So the stoichiometric coefficients give the relative amounts of reactants and products that you're going to get. So we already looked at this on Wednesday when we were balancing equations. This is the reaction that y'all did in lecture where you burned your magnesium ribbon with oxygen in the room. So we would say, I think, in blue is probably how I think of when I come up with these set of stoichiometric coefficients of 2, 1, and 2. I think of having like 2 atoms of magnesium combined with 1 mole of O2, 1 molecule of O2 to form 2 formula units of magnesium oxide. I think on the small scale. But we could scale this thing up, and those coefficients of 2, 1, and 2 respectively, they also apply not just on the small scale, but they apply to a larger scale. And that's actually, when we do stoichiometric calculations, what we're counting on. So the recipe, or the coefficients of 2, 1, and 2, we could actually say 2 moles of magnesium combines with 1 mole of O2 molecules to form 2 moles of MgO formula units. So that's what we're going to kind of count on using. So stoichiometric coefficients isn't a new word. Stoichiometric coefficients are the things that you changed in order to balance the equation. Okay? So I really think a balanced equation is great for giving the quantities, like I said, go back to the recipe thing. It gives you how much you need to react and how much you're going to form. Now, like I said, not only on a small scale, but also the moles of those things. Lots to feel out. Okay. So what we need to do today is talk about a type of chemistry calculation. It's a classic. My kids roll their eyes when I say it's a classic. A type of chemistry calculation called a stoichiometric calculation. And it's like kind of scaling the chemical reaction. Most commonly, the stoichiometric calculations go something like, remember yesterday you guys went from grams of NaHCO3 to ultimately grams of CO2. Okay, that was a stoichiometric calculation. Okay. Amount of, in this case, a reactant to amount of product. It could be the amount of a reactant to another reactant. It could be the amount of product to a reactant. Just 1 grams to another grams. But the amount doesn't have to be in grams. It could also be in moles. So the kind of scaling up of the 2Mg reacts with 1O2 to form 2MgO, the kind of scaling up, the 2 moles reacts with 1 mole to form 2 moles. Actually, we can, from the coefficients of a balanced equation, go ahead and come up with these things called stoichiometric ratios. And actually, a stoichiometric ratio is at the heart of grams to grams conversion. It's at the heart of a stoichiometric calculation, these ratios. And we create these ratios from the stoichiometric coefficients. So, here we go. Magnesium reacts with oxygen to form magnesium oxide. So it depends on what two things we're looking at. There's three things here. It depends on what pair of things we're looking at. So for instance, here's a bunch of different ratios. I actually have 6 ratios. This ratio is just focusing on what? The two reactants.
Magnesium, oxygen.
Yep, magnesium and oxygen, exactly. And the 2 for the 2 moles of magnesium came from the coefficient up there. And you guys told me, so this 2 ended up right there, and you guys told me that if there's no number here, that's implied 1. So that's where that 1 is. What's the relationship between these two? They're reciprocals, yeah, they're flips, exactly. Okay, so we can look at another pair. It just depends upon the calculation that you're supposed to get from what to what. So we could instead be looking at magnesium, one of the 2 reactants, and the product. And then we have this relationship of a kind of a 2 to 2, 2 moles to 2 moles. Okay. Sometimes students will say, Mrs. Snipes, you're just kind of wasting ink. Why don't you just put a 1 there? You know, relative amounts of 2 moles to 2 moles is the same thing as 1 mole to 1 mole. Well, I like this because I can go back to the balanced equation. I can see my number 2's up there, but it's the same diff. Okay. And the reciprocals are true. The last set would be, looks like the oxygen and the magnesium oxide. Okay, so we have these 6 different ratios, and we're actually going to use 2 of them to work a couple of problems, stoichiometric calculations. So, I hope you guys brought your calculators, because here in a minute I'm going to turn you loose, and you guys are going to be working your own calculations. All right. So I call this kind of we're going to start out with a baby problem. Okay, a little bit ago, do you remember where I said we go from grams of NaHCO3 to grams of CO2? And I don't know if you remember, but actually there's a couple of steps in between here, okay? But I want to start with kind of, I guess, a baby calculation. A lot of times, if I have an equation like that, I will pull the information from the problem and put it up on the equation. It really does me pretty well. So, for instance, how many moles oxygen? So I'll put question mark MOL for the oxygen. How many moles of oxygen is needed to react with 0.245? And that goes under my mg, 0.245 mole. It's just a way to kind of organize information. So kind of that's the plan. So that's actually the first question. And the second question, these are moles to moles problem. The second question are how many moles of MgO, so question mark moles, MgO, can be produced. Now, this is not written very well. It should say can be produced from the amounts above. How's that? Number 2 is basically piggybacking off of number 1. So it's not very well written. You wouldn't see like that kind of test. But bottom line is we're going to start with 0.245 moles of Mg. And we're going to actually, and we'll get into this on Monday, we're going to say sufficient O2, and this is problem number 2. So if I had those 2 problems, I'd probably put problem 1, and then problem 2. I'd superimpose it underneath there. All right. So we can go from moles to moles simply using one of those 6. We can work these 2 problems. It's really not too bad using one of those 6 ratios. Sometimes what I've done in the past is write A, B, C, D, E, F. So which of the ratios do we need to work this problem? And actually it's this one. Does this make sense? We've talked about using the factor label method, and we put units that we want to cancel in the denominator, moles of magnesium in the denominator. We put units we want to be left with in the numerator, moles of O2 in the numerator. What are these two numbers, 1 and 2? Well, they came from the balanced chemical, they're stoichiometric coefficients. So this is just a stoichiometric ratio, simply to bada boom, get from moles of magnesium to moles of oxygen. All right? The second one goes like this, where we're going to use a different ratio. Why? Because we're trying to get to something else. Again, we're starting with moles of magnesium. Moles of magnesium. I really love molar mass of magnesium. So we're starting with moles of magnesium, trying to get to moles of oxygen, magnesium oxide. So we put units of moles of magnesium at the bottom, units of moles of magnesium oxide at the top. What numbers go there for their, I usually put the units first, and then I go back and look at my balanced equation to plug in the coefficients. Okay, so for instance, for this guy right here, okay, this 2 came from this 2, and this 2 came from this 2. Okay, now I know that that's like 1 to 1, and it's not going to change your number, and you're right. But it's all about factor label. Here we go. So to work these two problems, these moles to moles conversions, the first one we put 0.245 moles of magnesium over 1. And then we plug in that ratio that has units of moles of magnesium cancel, leaving us with moles of, moles of O2. Okay, so we said the ratio from the stoichiometric coefficients is a 1 to 2, 1 moles of O2. All right, so I can about do that math in my head. Notice that we need to round according to significant figures. So we have 3 sig figs in the first term. The whole stoichiometric coefficients, no uncertainty. So no uncertainty brought by the 1 or the 2. Okay. Now that is like the heart of an ordinary stoichiometric calculation. Okay, that's the baby part. So let's work the second one. Second one, we started out with a 0.245 moles of magnesium over 1. And then we're going to go from moles of magnesium to moles of magnesium oxide. So this was that 2 to 2 relationship, my stoichiometric ratio. 2 moles of magnesium oxide are formed for every 2 moles of magnesium consumed, which means I should get the same number. I can do that one too. Okay. But notice that we can use the recipe as given by the stoichiometric coefficients as long as we're dealing moles to moles. That's wonderful. Okay. Not too bad. Well, we're going to take the same equation, a very similar problem, okay? But now instead of having moles to start out with, we have grams to start out with. And that's usually what it is. Okay. So the way this one works, I'll go ahead and superimpose it underneath the balanced equation. So what mass of oxygen, so question mark, grams now of oxygen is needed to react with 0.30 grams of magnesium. Okay? So we want to go from 0.30 grams of magnesium to so many moles of O2. We can do that. Just a minute ago, we went from moles of Mg to moles of O2. Now we wanted to go from grams of Mg to grams of O2. And I don't know if you saw how I kind of opened my arms. Okay, we did this, and now we're kind of starting with, instead of moles, we're starting with grams. Instead of ending with moles, we want to go to grams. Okay, so it just widened out the problem a little bit. Okay, so this is just to kind of emphasize that when we did those moles to moles problems, we could do the stoichiometric ratio. You can't use the stoichiometric ratio in just short and sweet in this problem. You have to do something on the front end and do something on the tail end is how I think of it. And that something is something that we've already been just talking about so far in this class. So we got to go from grams to moles. We can do that. How do we do that?
You have to find the atomic mass.
Yep, use the periodic table and knock out the molar mass ultimately of magnesium from its atomic weight. And then once we have moles of magnesium, then we can do what we just did, a stoichiometric ratio. And that will leave us, we will kind of that step right there is kind of linking from one compound to the other compound, relative numbers of moles. But the problem didn't ask for you to end with moles of O2. We wanted to go to grams of O2. And we know how to do that. How do we do that? Molar mass of O2, exactly. So this sort of pattern, for those of you who like patterns in chemistry problems, a lot of times chemistry problems are just a mishmash of everything. But if you want to go from grams of something to grams of something else, this pattern really works. So you'll need the molar mass of your first thing, and then link your first thing to your second thing using the balanced equation, and then use the molar mass of the second thing. All right. So do you guys already have these then? Did I knock out the molar mass of everything? We're going to work a couple of problems now. We're actually going to go from magnesium to oxygen is the first problem, and then we're going to go from magnesium to magnesium oxide. So kind of knocking out, like Joshua said, the molar masses of everything. We use the how much it weighs and change the units, basically. The decimal number for magnesium is 24.31. Makes a great password. I'm recording. Now I got to change all my passwords. All the thousands of people who are going to read it knows what my password is now. So we good with this? And this brings up a good point. If I have, like, I roll my eyes. If I have a series of stoichiometric calculations with the one balanced equation, sometimes, dang it, I'll just knock out my molar masses right at the very beginning. One of the things, and you're pretty good at doing this, is you have to show me your molar mass calculations. It's not just a blah. You have to show it to get full credit. Okay? All right. So let's work the first problem, and I'll show you what the second problem is here in a minute. So we're going to start with the mass of magnesium. That's that 0.30 grams of magnesium. Now, this is, and I kind of alluded to this before, the fact that we have two different species. We have magnesium and we have O2. We have Mg and O2. And we have masses in moles of both of them. We have to be explicit if you work it this way. I'm just going to string them up. So then we're going to use the molar mass of magnesium to get to moles. What does this next term look like? You want grams to cancel out for moles.
1 mole of magnesium.
Yep, 1 mole of magnesium over 24.31 grams of magnesium. Perfect. Can't remember if my builds do this, but sometimes I'll go ahead and cancel things that cancel. So right now I have moles of magnesium. So now what does the next term look like? I want to go from moles of magnesium to moles of O2.
So you just put your O2 in the
Put the O2 in the top, probably. So what will the number with the O2 be?
Yeah, I'm trying to find you.
So my hint was up here, so I'm kind of circling what those numbers will be.
Just
1. It'll be 1 mole of O2, and then what will be in the bottom?
The molar mass, or whatever's on here. 1
Nope.
mole and then
No, it'll be 1 mole of O2 in the top, and then, because we want moles of magnesium to cancel. This is where we go with our stoichiometric ratio.
and then you
Yep,
Mg.
2 mg, 2 moles mg in the bottom. Yep. So that is the skipping from magnesium to oxygen right there. But we're not done. The question didn't ask for moles of O2, it asked for grams of O2. So moles of magnesium cancel there. So now how do we get from moles of O2 to grams of O2? What does that look like?
Your
Molar mass, yep. I agree.
32.
Yep. 32.00 grams of O2 over 1 mole of O2, the molar mass. Exactly. Now, in working physical science problems, I really think you should let your units give you confidence. The fact that the units have canceled and we've gone from grams of magnesium to grams of O2, our units are awesome. And so we should feel warm and fuzzies about whatever our calculator spits back. Now, how do we need to round this? I heard 2, yes, 2 sig figs. Perfect. So what I got was 0.20 grams. Does it work? So that's an ordinary stoichiometric calculation, ordinary. And actually, she's emphasizing ordinary. There must be something extraordinary. And actually, Monday we're going to talk about limited supply stoichiometric calculations. That's Monday. So this is just your grams to grams. It's great. Okay, so let's do a similar thing. And if some of you are thinking, I bet there's an easier way to answer this question, there is. If you read the problem, now again we have 0.30 grams, and now we're question mark grams of MgO. Notice that, and this is what we're going to talk about on Monday, notice that the problem specifically takes the time to use the word sufficient. Amount of O2. So a minute ago, what did we say? How did we say how much O2 would react with Mg? What was the mass of that one?
32 something.
It was what?
The molar mass?
No, the mass of Og, grams of O2. Grams of O2. I said that wrong, I'm sorry. What grams of O2 will react with 0.30 grams of Mg? 0.20.
I don't know.
0.20 on your last slide. Remember on your last slide?
Yes, got it.
Okay, good. So for some of you who are thinking, well, can't we just say, you would be right. We'll talk about how that goes. Basically, if we say that matter, in this little chemical reaction, okay, the mass that you start with has to be the mass that you end with. Okay, you are truly correct. But let's get to that 0.50 grams using a stoichiometric calculation. So here we go. The first term is going to be the mass of the magnesium, 0.30 grams Mg over 1. And the first two terms are going to look identical to what we had before, aren't they? Okay, so we're going to go from grams of magnesium to moles of magnesium using the flipped version of the molar mass of magnesium. 1 mole over 24.31 grams of magnesium. Now, this will look different than that previous problem. What does this ratio look like? So we have moles of magnesium. We want to go to moles of magnesium oxide. Here's your hint. I know you're all thinking it. 2 over 2. Yep. You think so, Emily? I do too. 2 over 2. Okay. And those big 2's, came from right here. Excellent. So now we have units of moles of magnesium, but we want grams. So we're going to use the molar mass, aren't we? And so we have this pattern going. So we're going to use the unflipped version of the molar mass, which a few slides ago we said was 40.31 grams MgO over 1 mole of MgO. Units look great. How do we need to round it?
4, 2,
2, final answer.
yeah.
2 sig figs. See some of you kind of poking this into your calculator. And hopefully you get that number that I said probably should get. Sometimes students will say, well, Mrs. Snipes, if you had these questions back to back, can I just answer the second question if I know all the masses except for one and do well, this is called a mass balance, and I will never give it that to you. No, I'll never put you in that situation. Okay, but you probably would want to go through the stoichiometric calculation in case you made a mistake. Okay, so I've talked about a mass balance on either side of the reaction arrow. that's actually what this slide talks about. The first problem we did answered this whole O2 question. Okay, and then this then would be the MgO that's produced. Oh, I see. I guess, according to my slides, MgO2, MgO. You know, there's that song, there was a dog that had a name, Bingo was his name, O-B-I-N-G-O. I always think of that when I say MgO.
Just think the same thing.
B-I-C, B-I-N-G-O.
Was it the farmer that had a dog?
Oh, the farmer, what did I say?
There was a dog that had a son.
Yeah, the farmer, it was a farmer. So,
Just checking.
that's much better. So we'll do a few more, and then like I said, I'm going to kind of turn you loose to kind of work some problems. I won't take as much time here, okay? But again, we have two reactants going to form one product, excuse me.
Sorry.
Yeah. And we have coefficients of 1, 6, and 4. Okay, 1, 6, and 4. And it's balanced. And I tried to play, I played the one on the left, but couldn't get the one on the right to play the other day. But let's do a couple of calculations. Okay. And I'm going to go ahead and write underneath we're going to do two calculations. I'm going to write underneath what I'm after, what I have and what I'm after. It says what mass of P4, so question mark grams of P4, and this is the first problem, is needed to react with 1.25 grams of Cl2. Okay, so we can do that. And you probably already have the second one, and the second one goes something like this. What mass, question mark, grams of PCl3 will form with 1.25 grams of Cl2 and sufficient, there's that word sufficient enough, sufficient amount of P4. So you're like, well, we could do a mass balance to get the second one, and you're right. Okay, so we're going to work these two problems. In both cases, we're going to go from grams to moles, moles to moles, moles to grams. That's how I think of it. Okay. So do you guys have these molar masses? Okay, so I went ahead and did the periodic table, took 4 times what phosphorus is, and I got 123.88 grams per mole. I took 2 times what chlorine is, 2 times 35.45, and I got 70.90 grams per mole. And then for the PCl3, I took 1 times 30.97 plus 3 times the number for chlorine, 35.45, and I got a molar mass of 137.32 grams per mole. So again, just kind of showing your work kind of on the front end before you do your stoichiometric calculations. Okay, so here we go. Let the fun begin. So we're going to start with 1.25 grams of Cl2 over 1. Then we go to moles of Cl2 using the flipped version of the molar mass of Cl2, which we said was 70.90. So 1 mole of Cl2 over 70.90 grams of Cl2. Grams of Cl2 will cancel. Now, this is where we want moles of Cl2 to cancel, and we want to be left with, in this case, moles of P4. I'm going to emphasize this. So this is where I visit my Cl2, I put the 6 right there, and I visit my P4, I put the 1 right there.
Question.
Uh-huh. 35.45?
35.45 has 79.40 in the previous slide. Did I write that down?
Yeah,
Your second one, the 70.9 is right.
7090 is.
70.90, yep.
Okay. Just
Yep.
checking.
But did you you see where the 1 and the 6 came from for this part?
Yes.
Okay, good. So then we have moles of P4, and now we're ready for the molar mass of P4, which I cannot remember. It's 4 times 1 phosphorus, which looks like I had 123.88 grams per mole. So 123.88 grams of P4 for 1 mole of P4. Units of moles of P4 cancel out. And we have grams of P4, which is wonderful. And then how do we need to round this?
basically.
I'm liking 3 sig figs. So 0.364 grams P4. It just kind of give you hand cramps sometimes. It's like, oh my goodness. So let's do another one. Let's do that second part. So in the second part, we are gonna, oh, did you guys have this slide? Okay. So in the second part, we're gonna start with, we're going from grams of Cl2 to grams of PCl3. So the first 2 terms are gonna be the same, aren't they? So 1.25 grams of Cl2 over 1 mole of Cl2 over 70.90 grams of Cl2, that's the molar mass. So what does this ratio part look like? What do you think? What do you think?
Is it like the 4 over 4 then?
It's the 4 over what? Not 4.
4 over 6.
4 over 6. Yep, and units to go with that. Yep. It's 4 moles of PCl3 over 6 moles of Cl2. Exactly. So this 6 came from the coefficient in front of the Cl2. This 4 with the moles of PCl3 came with the coefficient from the PCl3. Perfect. And we did that, so now our moles of Cl2 cancel. We have moles of PCl3, and we're going to use the molar mass of PCl3, the non-flipped version, which is 137.32 grams of PCl3 over 1 mole of PCl3. Units of moles of PCl3 cancel. We're left with units of grams of PCl3, which is great. Rounding? 3, yep. So I got 1.62 grams PCl3. In this case, we can do a check. Okay. And they do, do they add up? 1.25 plus 0.364, does that equal? Okay, good. Okay, so this is where I want you guys to see what you can do. So let's limit it. I don't want you to do everything. Let's do 1 of 1 and 1 of 2. So let's see what I mean by that. You could be faced with a problem like this. Part of the problem in doing problems is understanding the problem. But if you do what I did, which is like kind of take the information and put it under the species it connects with, that's going to help you with other chemistry problems too. So 0.143 grams of O2. So what question 1 is, actually there's a 1A, 1B, there's a 1A and 1B. So basically it says what mass of each reactant reacted. So this would be 1A and this would be 1B. question mark grams, question mark grams. Those are two separate stoichiometric calculations. You would do one calculation to go from grams of O2 to grams of TiO2. That's one calculation. And you would do a second calculation, a B calculation, to go to, they're unrelated, by the way, as far as I'm concerned. They're separate stoichiometric calculations. To go from O2 to grams of BRF3. So I want to do the first one. And I want to do one of the next one. Let's look at what the next one says. It says, again, with that same amount of O2 produced, which of the other, how much of the other products would be produced? So I'm going to call this 2A, question mark grams. How much TiF4 could you get if you had 0.143 grams of O2? And here under the BR2, I'm going to put 2B, question mark grams of that product. Stoichiometric calculations don't have to go from a reactant to a product. In this case, we're going from the mass of a product to mass of something else. So if you guys, I'm going to turn you loose. The ones I circled, let's go for those. I'm looking for two stoichiometric calculations. Oh, and do you guys have this slide? Okay, good. You have all the molar masses? Okay, and you can work together. You can, I don't think surfing the internet's going to help, but. So we could do a mass balance, and it should be similar. If you do this check, if you're fortunate to be able to find all of the masses on either side of the reaction arrow and want to see if you have the same mass, don't worry if you're kind of off by a couple of hundredths of a gram, because it's from rounding. So don't freak out. Okay, so these will be due on Monday, Marvelous Monday. And I finally combined my folders. So let's see if they show up okay. Okay, so these are what they look like. I didn't look at them in my office. The delta, you see the triangle over the A, see it says A and it has a reaction. Anytime you see a triangle like that, that means heat. Okay, so it's just saying it's heating. Just like what you did in the lab. We could have used delta for your sodium bicarbonate when you heated it up in your evaporating dishes. So notice the first one, there's a couple parts to it. I went ahead and said what A is. A is how many moles of O2 can be produced by the decomposition of KClO3. I know a lot of words, right? But I love the equations. So go find the equation, put that mass under the, put that mass under the KClO3 and put question mark moles, okay? Notice my hint is basically you're not going to do a full-fledged stoichiometric calculation. You're going to stop just short of going all the way to grams. I know I said it's usually from grams to grams, but this one's grams to moles and moles to moles, and stop. Okay? B looks like this. It says how many grams of KClO3 must decompose to produce 50.0 grams of O2. Now in this case, what we do know is the grams of O2, and we're supposed to go to grams of KClO3. This is classic what you guys just did in lecture. So up there in blue, I kind of said what we've been doing. We use the molar mass of O2 to get to moles of O2. We use a stoichiometric ratio to get to moles, from moles of O2 to moles of KClO3. Then we use the molar mass of KClO3 to get to grams of KClO3. And then the last one picks on something else. If you read it a few times, you can kind of see in green what you got going. We have a mass of O2. You're supposed to get to the mass of KCl. Okay? So, like I said, sometimes the words, don't let the words foul you up. So the second one, again, we have a heated reaction that requires heat. Notice that under the water, they're saying excess, and again, we're going to talk about that Monday, but that just means simply focus on the Fe, okay, as that mass of Fe, how much mass of H2 will you get? That's A. Again, you can kind of see how I just take the blah, blah, blah words and pull it out and put it underneath the reaction. I just think it's so much cleaner. Okay? So they're all just like what we've been doing. So don't let the words foul you up, okay? Guess that's my urging. All right. Very good. That's all I have. Have a great weekend.